Once you realize that, you'll quickly realize that all you're trying to do in classification is you're trying to learn weight vectors that will correspond to boundaries between positives and negatives. So centroids is one possible way to learn such a weight vector, but you could try to learn it directly. And the boundary that comes out of our centroids is not a perfect boundary, right? It misclassified a positive example and it misclassified a negative example. And in this case, we could do better, right? We could learn a weight vector, we could learn a boundary that separates the positives and the negatives cleanly. And we should. One possible glitch, however, is when you're dealing with text, and text is generally linearly separable, there's going to be lots and lots of such boundaries. Right? So that red line is one boundary that separates positives from the negatives. This is another boundary, right? And in general, there is an infinite number of lines that you could draw between the positives and the negatives if they're separable. So which one should you choose? One really big idea that came out in machine learning a few years back is the idea of a margin or a buffer zone. Some of you are familiar with this already. The basic idea of a buffer, the basic idea of a margin is you don't just look for a boundary that tries to separate the positives from the negatives. You also try to put a little buffer zone around that boundary. And what you want is you want no examples, either positive or negative, to fall inside that buffer zone. So if you're thinking of an analogy, this is your North Korea, this is your South Korea, this is the border between them, and you don't want any of them coming very close to the border. So you'd like to create a buffer zone to keep them as far away from each other as possible. Or if you don't like Koreas, think about Russia and Ukraine, or any of the similar conflict situations. So you want a buffer zone between the positives and the negatives. And for this particular boundary, the buffer zone, that would be the buffer zone, right? In this it's parallel to the decision boundary, and there is no positive or negative examples anywhere within the buffer zone. So the buffer zone for this particular hyperplane is relatively narrow, but I could make it better if I came up with a different hyperplane, right? Now, why am I concerned with that? The reason I'm concerned with the buffer zone is because the points that I have here, they're just my training set. Right? These are the examples that somebody gave me of spam emails or non-spam emails, or tweets that will be censored and tweets that will not be censored. Tomorrow, I'm going to get a lot more data. I'm going to get my testing set. I don't have the labels for it today. Now, I assume that it's going to be distributed sort of kind of like the training set that I have today, but there will be some variation. So tomorrow, I'm going to get more positives and more negatives, but they're going to be shifted around in space. And if you come up with a hyperplane that has a large buffer zone around it, there is a smaller chance that the positive examples will creep from the new test from the new set that you see tomorrow. There is a smaller chance that the positive examples will creep into the negative territory, and negative will creep into the positive. So that's the idea for the buffer zone. Right. So you would like to find a hyperplane that has as large a buffer zone around it, or as large a margin around it as you possibly can. So really, you don't just want positive documents to have a positive dot product. You want that dot product to be above some threshold, theta for the positive, and smaller than minus theta for the negative. So there is a number of algorithms for learning such hyperplanes. These are known as large margin or max margin hyperplanes. The most well-known example is probably the support vector machine. That's what gives you the best classification accuracy for this form of solutions. They can be fairly slow to train, so you should never try to implement an SVM yourself. There are plenty of libraries around there, even though we'll talk about how you actually estimate support vectors today. There is another algorithm that we'll talk about in today's lecture that's called passive-aggressive. So It's completely opposite. It also estimates a large margin hyperplane, but it is a very fast algorithm. It's very suitable for streaming scenarios. So if you're trying to deal with millions of tweets, your SVM probably will not scale without massive hardware, but something like a passive-aggressive can be trained with very modest hardware. Its accuracy isn't always as high as the SVM, and we'll talk about the reasons for that. Now, before we start that, couple of sort of practical tips. For large margin classifiers, there's always nonlinear versions. They're a waste of time for text. Text is usually linearly separable because the dimensionality that you're working in is so ridiculously high. So any kind of feature selection or dimensionality reduction or LSI or topic modeling is going to be a waste of time. But things like TF-IDF weighting, so the basics that we covered in the course, they're actually quite useful. And in text, you always want to normalize for length. You typically normalize everything, all the vectors, all the documents to unit length.